Welcome to our maths lesson today. My name is Purity Anzelimo. Our topic for today is trigonometry. Trigonometry. That's our topic. And our subtopic for today, we are going to look at some transformations or just transformations of waves. Some of the transformations of waves. Transformations of waves. Transformations of waves. Before we get to the transformations of waves, I would like to do a reminder of what we had seen during the previous lesson, that whenever we have a general equation, whenever we have an equation y is equal to, let's say we have a cos bx, and you want to get the amplitude and the period, we say that the amplitude will be given by a. This is our amplitude. And again, when you want to get the period, you consider this, whereby now you talk of the period being 360 degrees divided by b, such that if you have y is equal to a half cos or even sine cos maybe 3x, when we have such, in this case a half becomes the amplitude. So the amplitude is a half units. And then when you want to get the period therefore becomes 360 degrees divided by 3, which is 120 degrees. Again, when you have, for example, y is equal to 3 sine 2x minus 80 degrees, and you want to get the amplitude and the period, again you ensure that you write it in this form, whereby we are going to have 3 sine, we can factor out 2 here, we remain with x minus 40 degrees. Then we come and say, let x minus 40 degrees be theta, such that we are going to have y being equal to 3 sine 2 theta. And therefore, the amplitude becomes 3. So the amplitude is 3 units. And our period, in this case, our period therefore will be 360 degrees. We divide by 2, that is 180 degrees. So that's how we go about getting the period and also the amplitude, even when we have not plotted or have drawn the graph. So I would like us to look at the transformations of waves. And I would like to do various examples so that you can get to understand how waves are transformed, or how do we describe the transformation. So I want us to compare, number one, I want us to compare the graphs of, we have the two, y is equal to 2 sine x and y is equal to sine x. We've been given in the interval that is 0 degrees up to 360 degrees. So that's what we have been given, and we have been told to compare the graphs. We are comparing these two graphs. We have this function and we have the other function. So we want to compare these graphs in this interval. So what we do, we need to plot these two waves on the same axis. So on the same axis, we plot the two graphs, that is these two waves. Then after plotting the two waves, then we'll be able now to compare. We'll be able to compare this function and the other function, that is the two waves, so that we can be able to describe the transformation. So in this, we start now, we need to plot, we plot the two on the same axis. On the same axis. So we plot both of them on the same axis. So we can start with this one, whereby we have y is equal to 2 sine x. So in this we require a table. We require a table for the values of x and the corresponding values of y. We can even have one table for both of them, because this is 2 sine x, the other one is sine x. So in this we have x, then here we have y, which is equal to sine x. Then on the other side here, so that we just have one table, we have y, which is 2 sine x. So in this we'll just be multiplying whatever we get here by 2, because this is sine x, this is 2 sine x. So we have our angle, 30 degrees, we have 60 degrees, 90, we have 120, 150, 180, we have 210, 240, 270 degrees, we have 300 degrees, we have 330, and finally we have 360 degrees. So we need to fill that table so that now we can draw the two waves on the same axis. So we have, that is the first one, we have sine 30 degrees, which is 0.5. Then here we are just multiplying this sine x by 2. So 0.5 multiplied by 2, we get 1, which is 1.0 to 1 decimal place. Then we have sine 60, which is, we can round it off to 0.87. So when we multiply that by 2, we get 1.73. We ensure that it is also into 2 decimal places. Then we have sine 90, which is 1.00. We multiply by 2. Then we have sine 120, which is again 0.87. When we multiply by 2, 1.73. So we have sine 150, that is 0.50. We multiply by 1, 1.00. Then we have sine 180, that is 0, just 0.00. Here we have 0 again. Then we have sine 210, which is negative 0.50, which here is negative 1.00. After multiplying by 2, we have sine 240, which is negative 0.87, and here we'll get negative 1.73. Then we have sine 270, that's negative 1.00, negative 2.00. Then we have sine 300, which is negative 0.87, negative 1.73. Then we have sine 330, which is negative 0.50, negative 1.00. Finally, we have sine 360, which is 0.00, 0.00. Then after having that table, that is for sine x and also for 2 sine x, then we are going now to plot the two on the same axis. When we are plotting on the same axis, we plot each at a time. So we are going to plot each one of them at a time. So we plot one, we name it, then we plot the other one and name it to avoid the confusion. So we are going to have the two axes, the x, where we have, this is the y-axis, where we have the highest being 2. So that's what we have. Then we have the x-axis, that's from 0 all the way to 360 degrees. So here we have 1, then we have the highest being 2. So we can have here 0.51, 2, 0.51, 1.52. So we can have this our 0, we have 1 here, this is 0.5, 1.5, we have 2.0, this is 0.5, negative, then negative 1.0, negative 1.5, and negative 2.0. Then here we have from 0 to 360 degrees. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. So that's what we have. So we have 0, we have 30 degrees, 60 degrees, we have 90, 120, we have 150, we have 180, 210, 240, 270, we have 300 degrees, we have 330, then we have 360 degrees. Then now we need to plot those points. So we can choose to start now with sine x, whereby we have 30 degrees, 0.5. We need then to start with 0. We started at 30, so we need to start at 0. We need to add the 0 bit because it is from 0 to 360. So we need to add the 0 degrees. The 0 degrees. So we can have this part for the 0 degrees. This is 0 degrees. This is our x. This is our y, which is sine x. This is our y, which is 2 sine x. So we have sine 0, which is equal to 0. So here we start with 0.00, 0.00. So at first we have 0 degrees, then 0, 0, 0. Then we have 30, 0.5. 30, we have 0.5 at that point. 60, we have 0.87, almost 1, 0.87. Then we have 90, we have 1. 90, we have 1 here. Then we have 120, 0.87, it's there. Then we have 150, we have 0.5, which is here, 0.5. Then we have 180, we have 0. Then 210, we have negative 0.5. So we have our 0.5, negative 0.5 somewhere here. Then we have 240, negative 0.87, which is almost 1. So it's somewhere here. Then we have 270, we have negative 1. Negative 1 is here. Then we have 300, negative 0.87. Negative 0.87 is here. Then we have 330, negative 0.5. 330, we have negative 0.5. This is 0.5. This is 0.87, almost 1. So it's here. Then we have negative 0.5, which was this on 210. So we have it here. Then 360, we have it as 0. So now once we plot that for the first function, we need to join and name that curve or that wave. So we are going to have it this way. This is what we have for our curve. 240 is supposed to be negative 240. We have negative 0.87. So this is 0.87. So we take it a bit down. 0.87. And this one is at the same level here. For 300, we still have negative 0. That. So we join it. using a smooth curve. So this is what we are going to have. So for this 240, which is supposed to be negative 0. Okay, so it's supposed to be down here. So we have it at that point. So we have our curve. That is the first curve that we are going to have, whereby we have, therefore, we can name this y is equal to sine x. Then we need also now to plot the other points for y is equal to 2 sine x. Again, we start with the 0. We have 0. So the first one again is 0, 0. Then we have now 30. We have 1. 30 here we have 1. So we have it up here. We have 1. Then we have 60. We have 1.73. 60. We have 1.73, which is somewhere here. Then we have 90, that is 2. 90, we have 2 at this point here. Then we have 120, 1.73, which is here. Then we have 150, we have 1. We have 1 for 150, somewhere there. Then 180, 180, we have 0. So again at that point. 210, we have negative 1. 210, we have our negative 1. Negative 1. In the graph paper, it's very clear. Then 240, we have negative 1.73. So it's somewhere here, negative 1.73. Then we have 270, we have negative 2. Negative 2 is down there. So we have that. Then 300, we have negative 1.73, which is here. 330, we have negative 330, we have negative 1, and our negative 1 is here, negative 1. Finally, 360, we have 0. So again, we come and plot those points so that we can get the other curve. We are starting from 0 here, moving to 30, 60, to 90, to 120. Then we have, after 120, we have our 150. Our 150 is supposed to be 1. 150 is here, and we are supposed to have 1. So we have 1 at this point here. So we have 1 there. So we join it using a smooth curve. So we get that point. Then we move on to 180. It is at the same point, which is 0. Then we move on to the other parts all the way to 360 degrees. All the way to 360 degrees. So that gives us the wave. That's our wave. Then we need to come and name this wave. We need to come and name the wave. The wave is y is equal to 2 sine x. In the graph paper, you can be able to plot it very clearly because you have the parts, you have the squares. So this is our other wave, that is y is equal to 2 sine x. So we have the two. We want now to compare the graphs of y is equal to 2 sine x and y is equal to sine x. And we have seen the first thing is to plot the two on the same axis, and that's what we have done. After plotting the first one, we name it. Then after plotting the second one, again we name it. Now I want us to compare one. we'll compare the period, we'll also compare the amplitude. So we can start with the amplitude. And we can see for this wave, that is y is equal to sine x, the amplitude is 1, the maximum displacement is 1. So we can say for y is equal to sine x, the amplitude is 1 unit. The amplitude there is 1 unit. Then for the other one, we can see on the other one, the maximum displacement is on either side is 2. This or that. So for y is equal to 2 sine x, the amplitude here is 2 units. The amplitude is 2 units. So we are comparing, we've compared the amplitude. We can also compare the period. The period, we can start with the first one, that is for y is equal to sine x. We need to know the period, and we think that the period, we compare one complete oscillation. So if we look at y sine x, so we are going to have it, this is a half, then we have the other part here. And therefore our period is 360 degrees. So for this, the period is 360 degrees. Then for y is equal to 2 sine x, again we need to come and consider the period from this. So we have it, this is a half of an oscillation, then we have the other one. So again, the period for y is equal to 2 sine x, again here the period is 360 degrees. So we've compared the amplitude, we've also compared the period. Now we also need to ask ourselves, how can we obtain the wave y is equal to 2 sine x from y is equal to sine x? So how do we obtain? For us to obtain y is equal to 2 sine x from y is equal to sine x, there is a transformation. And as we can see, you can see at this point they are the same at this point and at this point. But you can see for this one, it is at 1, while for y is equal to 2 sine x is at 2. And therefore we say to obtain y is equal to 2 sine x, we stretch the y is equal to sine x by the scale factor 2. The scale factor here is 2 because this is 1. When we want to get 2, we are multiplying 1 by 2. So we stretch it by the scale factor 2. That is parallel to the y-axis with the x-axis invariant. The x-axis is not varying with the x-axis invariant. So the transformation here, that is to obtain this from y is equal to sine x, we have a stretch of scale factor, 2, that is parallel to the y-axis with the x-axis invariant. And this is now the transformation. It is a stretch, there is a T here. We have a stretch of scale factor 2 that is parallel to the y-axis, but then with the x-axis invariant. This is a stretch. A stretch of scale factor 2 parallel to the y-axis with the x-axis invariant. So that is the transformation that we have in this. We have compared the amplitude, one is 1, the other one is 2. The period is the same for both, which is 360 degrees. With that, now the transformation, we have this y sine equal to sine x. when we want it now, when we want to obtain y is equal to 2 sine x, we stretch it where with a scale factor 2 with the x-axis invariant parallel to the y-axis. So like us to do another example for again transformations of waves. So we see how can we obtain one wave from the other. So in this one, we've been given the following. Number 2, by drawing the waves for y is equal to sine x and y is equal to 2 sine a half x on the same axis, describe, in this one we are told now to describe how to obtain y is equal to 2 sine a half x from y is equal to sine x. Describe how to obtain that. Then we are also told to state the period and amplitude. State the period and the amplitude of y is equal to 2 sine a half x. So that's what we have been given in that question by drawing the waves for y is equal to sine x and y is equal to 2 sine a half x on the same axis. Describe how to obtain y is equal to 2 sine a half x from y is equal to sine x. Or simply we are told to describe the transformation as we are obtaining this from y is equal to sine x. Then we are told also to state the amplitude and also the period of y is equal to 2 sine a half x. So in this, we again come to plotting the waves. We plot each at a time. We can choose in this case to start with y is equal to sine x, and therefore we require a table for that. We require the table whereby we have x here, then we have y, which is sine x. Our y is equal to sine x. Then we can have the range from 0 to 360 degrees. So we have 0, we have 30, 60 degrees, we have 90 degrees, 120, 150, 180 degrees, we have 210, 240, 270, we have 300, that is again for x. Then this is our y, which is sine x. We have 300 degrees, 330, and finally we have 360 degrees. So we first fill that table, then we first plot the wave y is equal to sine x. We are plotting each at a time. So we have the sine 0, which is 0. So we have 0. We have sine 30, which is equal to 0.5. We have sine 60, which is equal to 0.9. We can round it off to 1 decimal place. We have sine 90, which is equal to 1. We have sine 120, which is again 0.9. Sine 150, 0.5. We have sine 180, which is 0. Then we have sine 210, negative 0.5. Sine 240, negative 0.9. Sine 270, we have it as negative 1. Sine 300, we have it as negative 0.9. Sine 330, we have negative 0.5. and sine 360 is 0. Then we need now to plot that. We start with that. So we can have the same, whereby now we just need to plot. Actually, we had for sine x, and I've just continued with it. So this is what we have. We use the same axis to plot the two curves. So we are going to start with sine x, then we plot the other one, which is 2 sine a half x. So in this is what we have. So we have it that way. This is 150. We have 180. We have it at that point. So this is our 30th increase. We have 180, 240, 270. This is 300, 330. Then finally we have 360 degrees at that point, 360. So we plot that once again, 0, 0, 30, 0, 0, then 30, 0 0.5, 30, 0 0.5. We have 60, that is 0 0.9, almost 1 here. Then we have 90, which is 1. 90, we have 1. Then 120, again we have 0 0.9. Then we have 150, which is 0 0.5 at this point here. Then we have 180, which is 0. 210, we have negative 0 0.5, which is this point here. Then we have negative 0 0.9, almost 1 here. Then we have negative 1 for 270. We have negative 1. Negative 1 is here. Then we have for 300, negative 0 0.9. Then we have negative 0 0.5. Negative 0 0.5. And then we have 0. So we plot that once again. So this is the curve that we are going to obtain. In your graph book, it should be very smooth. So this is what we have for the curve. And then we require now to come and name it. After plotting, we need to name it. So that's what we have for our curve. Y is equal to sine x. Then we require now the other table for y is equal to 2 sine a half x. So we require that table so that then we can plot it. So in this case, we have y is equal to 2 sine a half x. So in this again, we have the same values of x. Then here now we have our y is 2 sine a half x. So we are going to have it this way. We have x here. Then we have y. In this case, we can start with the first part whereby we have a half x. We can have a half x here. Then after having a half x, we can have sine a half x. And finally, we have 2 sine a half x, which is our y. So we move it. We have 30 degrees. We have 60 degrees. 90 degrees. We have 120, 150, 180 degrees, all the way to 360 degrees. So in the other part here again, we have the values of x. We have a half x. Then we have sine a half x. And finally, we have 2 sine a half x, which is our y. So in this again we continue, 210 degrees, we have 240, 270, we have 300 degrees, 330, and finally 360 degrees. So again we need to fill that table. In this first part we have a half of x, so a half of this is 15, a half of 60, a half here is 45, a half of 120, a half of 150, that is 75, we have 90 degrees, here we have 210, we divide again by 2, that is 105 degrees, 120 degrees, 270 divided by 2, we have 135 degrees, here we have 150 degrees, 165 degrees, 180 degrees. Then now we will need to get the sine of this, sine a half x. So we have the first one, sine 15, which is 0.26. Then we need to multiply it by 2, which is now 0.52. Then we move on to the other one, which is sine 30. Our sine 30 is 0.5. So then we multiply by 2 and get 1.0. Then we have sine 45, which is 0.71. When we multiply it by 2, we get 1.41. Then we have sine 60, which is 0.9. Here we get 1.80. Then we have sine 75, which is 0.97. When we multiply it by 2, we get 1.93. We move on to sine 90, which is 1, which is multiplied by 2. Then we have sine 105, which is 0.97. Then we need to multiply by 2 to get 1.93. Then we have the sine of 120, which is 0.9. We multiply by 2, 1.80. Then we have sine 135, which is 0.71. Again, when we multiply this by 2, we get 1.41. Then we have sine 150, which is 0.5, which will be 1.00. Then we have sine 165, which is 0.26, multiplied by 2, 0.52, and finally 0.00, 0.00. So with that again, we need to plot the same on this same axis so that now we can be able to describe how y2 sine a half x is obtained from y is equal to sine x. So we have here 30 degrees, 0.52. We have 30 degrees and then 0.52. It's a bit higher than this at this point. Then we also have our 0 degrees. Our 0 degrees, we forgot to put the 0 degrees here. A half of 0 is 0 again, and the sine a half of x, which is 0, is 0. So here again will be 0. So for 0 we have 0, 0. At the first point the 0, 0. Then we have 30. Then with the 60 degrees we have 1. With the 60 degrees here we have 1, which is here. Then with the 90 degrees we have 1.41. We move on to 1.41 at this point here. Then with the 120 degrees we have 1.8. We are moving close to 2. We have it that way. Then at 150 degrees we have 1.93. 1.93, somewhere there. Then we have 180, we have it at 2. So at 2. at this point here. Then we have 210, which is 1.93. 210, we have 1.93, which is at that point. We have 240, 1.8, and our 1.8 is here. Then we have 270, which is 1.41, 1.4, which is here. Then we have 300 increase, which is 1. 300, here we have 1. Then we have 330, which is 0.52, which is this point here, 0.52. And finally, we have 360, which is 0. So again, we come and plot that curve, whereby we are going to have it this way. Plot the curve smoothly. So this is what we are going to have up to 360 degrees. So that's what we have for the curve. And then we need to come and name it. Y is equal to 2 sine a half x. Sine a half x. So that's what we have for our second curve. And now we need now to describe. So we have the two by drawing this. Describe how to obtain, how can we obtain this from y is equal to sine x. So here we have the first part here, we have a stretch with the y-axis parallel with the x-axis invariant. Because we have this part, you can see we are moving from 1 and this one being pulled to 2. So the first one will be a stretch. There is a stretch of scale factor. The scale factor, we have 1, then 2, so it is a scale factor of 2 with the x-axis invariant. That is 1. Then you can also see in this one we have 2 of them, but in this we only have 1. So this is a complete oscillation, but this is half of the oscillation. So we can also say we have another stretch, in this case now with the y-axis invariant. So it is followed by another stretch, in this case parallel to the x-axis, and of scale factor. The scale factor here again it's 2 because we have 1, 2, when we have this is 1, with the scale factor 2 and with the y-axis invariant. So those are the two transformations. We have the first one, a stretch of scale factor 2, that is with the parallel to the y-axis and with the x-axis invariant, followed by a stretch. You can see in this one again, followed by a stretch parallel to the x-axis of the scale factor 2, again on this side now with the y-axis invariant. So we had been told to describe how to obtain this from y is equal to sine x. So from this. So the first one is the first stretch parallel to the y-axis of scale factor 2, then followed by another stretch parallel to the x-axis and of scale factor 2 with the y-axis invariant. Then again, we have also been told to state the period and the amplitude of y is equal to 2 sine a half x. So in this we can see the amplitude, the maximum displacement here, which is 2. So the amplitude for this wave, the amplitude is equal to 2 units. Then we've also been asked about the period. In this we can see we only have half of the oscillation. So we can simply come and use the formula whereby when we have this, when we want to get the period will simply be equal to 360 degrees divided by our 1p here, which is a half, which will be 360 degrees times 2 over 1, which is 720 degrees. So the period is 720 degrees, so you can simply say this is half of the oscillation, so multiplied by 2, it will be 720 degrees. So those are some of the transformations of waves. We'll also look at more examples whereby now we have an equation like, for example, y is equal to sine x, and we have another one, y is equal to sine x plus something like 45 degrees. We'll also come to that whereby we'll also be able to describe that transformation. I would like you to do the following question on transformations of waves. I'd like you to draw, you are drawing on the same axis, so the exercise. Draw on the same axis the graphs of, in the first one we have been given y is equal to cos x and y is equal to cos adjacent x, and the range is from 0 degrees to 720 degrees. Then part B, we have y is equal to sine 2x and y is equal to 4 sine 2x, and the range here is from 0 degrees to 360 degrees. Then the question, in each case, describe the transformation, that maps the first graph onto the second. So in this, you draw on the same axis, you draw this and this. Again for this one on the same axis, this and this. And in each case, you describe the transformation that will map the first graph onto the second. So you describe that transformation just the way we have described here, the stretch and all that. So that during the next lesson, we'll also be looking at more transformations, whereby we'll be looking at a case when we have this case, whereby we have sine x and sine x plus a certain angle. Thank you. Let us meet during the next lesson.